do now is hopefully finish up chapter 14. Remember this? If you have any notes?
Yeah, change.
Yeah. The change in enthalpy of a reaction, remember what the superscript O stands for? Standard conditions, yeah. So change in enthalpy of reaction is equal to the change in internal energy of the reaction plus, what's that last part? Then that's supposed to be a nu, delta nu. Remember what that stands for? That's the last, I think the last thing I probably did last time. It's the change in the coefficients of the moles of gaseous products and reactants. Remember how I developed that? No. Well, okay. Where I started from was that look familiar? Delta V. And I showed you that PV equals nRT basically, right? Pressure's constant, the volume's changing, temperature's constant, number of moles is changing, right? Right? Is that okay? And I showed you that because the volume of a liquid or solid changes negligibly compared to how much the volume of a gas would change, that the delta N is basically the change in the number of the coefficients of the gaseous species in the reaction. That's what it means. And so what I was going to do is use this to compare delta H and delta U for reaction frequency.
Excuse me, I was wondering if anyone found any sheets of paper there. Just in the middle. One more. Thanks a lot. I'm sorry. So, for example, the reaction of hydroxylic acid with nitrogen monoxide.
make hydrogen peroxide and nitrogen gas. Change in enthalpy for that reaction is negative 96.3 kilojoules, as written. And this is at 25 Celsius. What I'm going to do now is calculate delta nu RT, plug it in here, and see how delta U compares to delta H. You guys see what delta nu is for this reaction? 2. 4 gaseous products. That's not gaseous, that's an L, so you ignore it. And 2 moles of gaseous reactant, so it's 4 minus 2 is 2. You guys clear on that? Go at 4,095 or so. Did you guys get the same number? No? Yes? So what does this mean? Well, you can interpret this over here as the PV work, the amount of work that's done in this reaction.
Where'd the moles go?
It's 2 moles here. Right? So, yes.
Where'd you get the 8.3?
That's R. And I used 8.3145 joules per Kelvin mole because I knew I wanted joules in this workout. Any questions? Did you guys get the same number? Did you try? So, one way, if you look at this over here, what we just calculated was this, delta nu RT, which is equal to, or approximately equal to P delta V. P delta V is just negative the work, right? PV work. So, in this energy balance here, the change in enthalpy is going to be equal to the change in internal energy plus the work, right? So, here, rearranging it, we know what the change in enthalpy is. Like 900, negative 901 or so, right? So, a couple reasons why I did this. First of all, I want to show you that most of the time, these are reasonable numbers, and the amount that the delta H and the delta U differ is usually relatively small, right? 10% of delta H would be about 90, right? That means 1% would be about 9. This is, just above half of a percent then. Not much. So they're pretty similar. Also, the physical interpretation. What does that number mean? Well, the change in internal energy, that's, the change in all of the energy, right? All the kinetic and potential energies of the particles that make up that system. At constant pressure, if we measure the Q, the thermal energy transferred, that's this. And that's what we got over there, right? Remember, delta H is Q sub D. The change in enthalpy is equal to the thermal energy transferred at constant pressure. The change in internal energy is a little bit more. That means that some of that energy had to go somewhere else. Where do you think that went? Okay, that difference between the 896 and the 901. The 901 is the change in internal energy, right? It's internal energy after minus internal energy before. You release that much internal energy. Going in, the amount that went into thermal energy, which is heating the environment, was the 896.
This is light.
What's that?
Light.
Light? No, we didn't take light into account. You're thinking of what did it do, right? Remember this over here? What's this again? Not sure. 2 moles of gas to 4 moles of gas. Is that going to expand or contract, do you think?
Expand.
Probably going to expand, right? Because you have more moles of gas on the product side than the reactant side. Assumes, same temperature and all that, right? That makes sense to you guys? More gas, bigger volume, right? How does something expand? What's that? Well, that's one way to make it expand. But when it expands, it has to do work on the surroundings. What's that? The pressure is constant, right? So this is that movable piston kind of picture, right? Pressure's not changing. Volume's changing, right? It has to, because we have more stuff in there. Keeping it at the same pressure and the same temperature, the only way that we can put more stuff in there is to expand the volume. Does that make sense to you guys? And the only way you can expand the volume is if you do work on the surroundings. So the picture here is the picture that I tried to start you out with. That piston in the cylinder, the movable piston, the massless, frictionless piston, remember that picture? Moves up and down. And it moves against the external pressure, whatever the atmospheric pressure is. It's constant, that's all we really care about here. So we start out on the reactant side, liquid hydroxylic acid, very small volume, right? It's a liquid, it's not going to take up much volume, relatively speaking. And some nitrogen monoxide, that's the gas. Reaction happens, we make some liquid hydrogen peroxide. Again, it's a liquid, the volume's not going to be much different. Now 4 moles of nitrogen gas. So basically, in terms of volume, we went from 2 moles of gas to 4 moles of gas. And again, we're assuming the same conditions, same temperature, same pressure, right? The only way that can happen is if there's more room, if it expands. And the only way it can expand is if it does work, if the pressure is constant, right? It is. Does that make sense? That work, okay, so there's 2 places. Remember the first law of thermodynamics? There's 2 places that, there's 2 modes with which energy can be transferred into or out of a system. Delta U equals Q plus W. Thermal energy and work. The energy that's transferred as thermal energy is this much. We're at constant pressure. The amount of energy that's transferred at work, as work, is this much. Make sense? Is work, let me make sure, is work positive or negative for this process as written? Whoever said negative is right, yeah. Right, because it's doing work on the surroundings. This system, this reaction, has to expend energy to expand the volume, has to do work, right? And that's why the change in enthalpy is not as great of magnitude as a change in internal energy. Some of that internal energy, this much, is spent as work to expand the volume. You guys see that? So, again, 2 points. That is, actually the mechanics of it, is how to do this calculation, because it's important, you should be able to do it. Second of all, what it shows you is the relative magnitudes of delta U and delta H. Most of the time they're pretty similar. A lot of times we just say they're close enough, we just call them the same thing. Say they're approximately the same. But also the interpretation, what it means, right, physically. Next topic. You guys remember what it means to be a state function? Something with a state function, what does that mean? Doesn't matter how you got there, right? It just matters what state it's in. And I told you guys that enthalpy is a state function, which means that for the change in enthalpy, for any process, any chemical reaction, the only thing that matters that affects its value, the change in enthalpy, is where it started and where it ended up. Doesn't matter what path it took to get there, right? Because that's true, we have Hess's law. We can use Hess's law. There's a couple of forms we're going to see when we start out this stuff. nitrate decomposes, apply some heat to do it, makes nitrous oxide and liquid water. And let's say we wanted to figure out what the change in enthalpy for this reaction was. If we knew these numbers that I gave you right here, we can use the fact that enthalpy is a state function to calculate the change in enthalpy for the reaction as written over here. And all you have to do is manipulate these equations, these chemical equations, so when you add them up, they're equal to, you get that equation over there. And so when you're adding equations, right, when you manipulate them, you can manipulate them. You just have to know that if you reverse the direction of the arrow, the change in the sign for the change in enthalpy changes, negative to positive, vice versa. If you multiply the coefficients through by some number, you also multiply the change in enthalpy through by that number. So what we want to do is we want to manipulate these guys so that we get this equation right here. What do you think we should do with the first one? Over there. What I see, okay, what's unique to this equation here that I don't see in the others is the ammonium nitrate, right? So that's what I'm going to focus on. Where do I have ammonium nitrate over here, and how many? Well, I've got one, just like there. But here, the ammonium nitrate is on the reactant side. Over there, it's on the product. So what I want to do is reverse the equation, right? So what I do, get this. Delta H, it's the same number. I didn't multiply anything, but it's the opposite sign, so now it's positive. What about the second one here? What's unique to that? You know, which species that's over there? Which one is in here and only here that's also over there? That's not in these two right here. Nitrous oxide, right? So I'm going to focus on that. I have nitrous oxide on the product side over there. I have it on the product side here. That's good. But the coefficient's different, right? Over there it's a 1, here it's a 2. So that means I want to multiply the coefficients by 1/2, which means I also multiply delta H by 1/2. And what do you think about this last equation? What's only in, what's in this equation but not in these other two? That's over there.
The water.
Water, right? And so we have 2 here and 2 there. It's a product here and it's a product there. So we can just write it down as it is. Now we're going to add these equations. When you add chemical equations, it's just like adding algebraic equations. If something appears on the left-hand side in one equation and on the right-hand side in another, it cancels. If it appears on the same side, then it adds. So let's see. Looks like nitrogen cancels. The hydrogens, yeah, 2H2. You guys see how we do this? Anything else cancel?
1/2 O2.
We've got 3 halves O2 over there, right? We have 1 here and 1/2 here. That's 3 halves. You guys buy that one? So this will cancel with that. Anything that didn't cancel, we just carry on down. Over here, it's just ammonium nitrate. Over here, we have nothing from there, nitrous oxide. It's exactly what we wanted. And then all you do to get the delta H for this reaction is add up these delta H's. So negative 124.4 kilojoules. You guys see how that works? And the reason we can do that is because enthalpy is a state function. Basically what we're saying is, even though this isn't how this reaction occurs mechanistically, we're saying it doesn't matter. We're going to make up sort of an imaginary path. We're going to take the ammonium nitrate, decompose it into nitrogen, hydrogen, and oxygen, then take some of that nitrogen and oxygen, combine it and make nitrous oxide, and then take some of the hydrogen and some of the oxygen, combine it and make water, right? And end up with the same products. That's not how it really happens, but it doesn't matter. As long as we can find some path whose delta H's we know, because enthalpy is a state function, set it up, get the delta H.
Question.
Yeah.
On that equation that you added, where did the 3 that was over the 2 go?
The 3 halves? This is 3 halves or 1.5 moles of oxygen on the product side. Here, we have 1/2 mole of oxygen in the reactor side. We also have 1 mole of oxygen. So this adds up to 1.5 in 3 halves. Any other questions? there are, okay, the molar enthalpy of formation, we define that first. The symbol for the molar enthalpy formation is delta H. Under standard conditions, superscript O, F for formation. What it is the change in enthalpy of reaction for the formation of 1 mole of a substance from its elements in their elemental form. What that elemental form means is that the 7 diatomic elements are, diatomic, so on. For example, change in enthalpy of formation of this molecule is described by the formation of 1 mole of this from its elements. So what are the elements involved? Carbon. What's the elementary form of carbon? Do you remember? What are the possible forms of carbon? Diamond, graphite. Right, remember those? It's been a while. Yeah. The elemental form, the standard state of carbon is graphite. What about hydrogen? What's its elemental form? H2, and it's a gas, right? And what else? O2 gas. Balancing it, 3 carbons, 8 hydrogens, so 4, 1 oxygen, so 1/2 here. It's defined as forming 1 mole of the substance, so you always have 1 mole, and it actually matters what state it's in. 1 mole of the product, and use whatever coefficients you need to balance the reactants. There are tables and tables of enthalpies of formation, or heats of formation, also called heats of formation. And you can look them up. And that's really nice, because one form of Hess's law says this. This is probably the most useful for you guys.